So now we have three different types of material that we can recognize thanks to quantum mechanics: the insulator, the conductors, and the semiconductors. So we have spoken about the energy of the electrons, and now we have to say that electrons also have a property which is called charge. So if we take the energy of an electron in two different conditions, let's say A and B, and we divide by the charge of the electron, so by definition we have this thing which is called voltage. So the voltage is a delta V, meaning that it's a difference, and it's the difference of this type of ratios. So for the first time in this course we introduced the concept of voltage. Let's have a better look. So let's summarize a couple of fundamental facts about the so-called theory of electromagnetism. So now we go a step backwards in the sense that the electromagnetism has been developed before quantum mechanics. Nevertheless, let's analyze a couple of facts. If I have a particle having a certain charge, we call Q this charge, then we can find that two particles close together can attract or repel each other. We can measure the force between those two particles, and we can find that if we define another quantity, which is this quantity E, not to be confused with the energy, and we call this quantity electric field, this quantity allows us to evaluate the force between two particles, one having charge little q, the other one having charge big Q. This is the electric field, we say generated by this big charge Q, and the other charge is subjected to the field generated by Q, producing a force between the charge which depends on the reciprocal of the square of the radius, which is the distance between the two charges. It's a thing that is similar to the gravitational law of Newton. It's exactly the same basically, but we are not speaking about the force of gravity, but a different type of force, which is called the Coulomb force. It's similar but not exactly the same, because as opposed to the gravitational force, which is something totally different, the most peculiar thing is that the charge can be either positive or negative, while the mass is always positive. We don't have repulsion between masses. And this perfectly matches the experiments that have been done a couple of centuries ago at least, and they were very difficult because accumulating charge is not an easy thing, at that time. So they were doing strange things like rubbing glass rods with a piece of wool or with the fur of a cat, and try to accumulate charge in metals, but this charge can be easily depleted if you don't know the difference between insulator and conductor and all these kind of things. But in the end, with this very delicate experiment, they were able to confirm this Coulomb force law. So attraction and repulsion. But this is not the only thing that we can do with electrical charges. We can also create circuits. The most simple circuit you can create is try to make electrons, and at the time when the ancient experimenter tried this, they didn't even know what an electron is, they didn't even know they existed. So the second, let's say, simple thing you can try to do is to try to make charges flowing into a piece of metal, a wire, we will say today, metallic wire. And then you see an interesting thing. Now we study currents which are charges that are moving, while those other experiments were electrostatic, basically. So the charges were accumulated in a place, but they didn't move. So when you move charges, you have a so-called current. We indicate this current with the symbol I. We can define again another field. This time we call it magnetic field. And this field has the property that if you make a current loop like this, with this verse of let's say gyration, and another one like this with this verse of gyration, there is again a force which does not depend on the charge deposited on this loop or on this loop, but it depends on the intensity of the current. So this is the force, just to understand better, that makes the needle of a compass rotating. So the electric field is something that attracts and repels charges. The magnetic field is something that impress a torque on the needle of a compass. Again, very interesting theory. We don't want to go into the details of this, we don't have time. But I want to mention one thing. Before they were able to do these experiments, magnetic experiments, they need a source of current. And it's not possible to create a significant amount of current before you have this. You need to invent the batteries in order to create a substantial amount of current, in order to be able to observe magnetism as the result of a current. And you probably also need to have this. That one you have seen is the pile. This one is a battery of piles, the one that just yesterday I replaced on my UPS at home. So an array of batteries, and then if you connect a wire like this, then you will have an enormous amount of current. Basically, these batteries is the fundamental thing that made people moving from the so-called electrology to the electronics. If you can't produce currents, we can't do anything basically in electronics. So to complete this picture, I want to mention the fact that all this thing has been extensively studied in a very beautiful theory which is called the electromagnetism, and the ultimate results of this theory, which takes into account various aspects also about relativity, is the Maxwell equations. So the results of the Maxwell equations, we will mention this in the end of the course when we will be speaking about electromagnetic source of noise. The result of the Maxwell equation can be summarized by saying that the electric and magnetic fields are not separate, but they are deeply interconnected, in a phenomena that is the electromagnetic wave propagation, which occurs in vacuum at a speed which is c, the speed of light, having a specific value, and those two things here are constants which are strongly connected with the magnetic field and with the electric field. I say this also to mention one other thing. In all this course, we will never speak about radiation. So electromagnetic waves radiated by antennas or such kind of things. We will always concentrate into circuits which are made by so-called lumped elements, so tiny things which are like small modules. So all the properties of those tiny things would be somehow embedded in those things, will not expand around the space. We will always stay in a region of space according to the wavelength of any possible electromagnetic wave, which is called near field. So where every time delays are compensated, everything is instantaneous, let's say. So we have a little bit of time, so let's start introducing the fundamental components of electronics. The battery is the one that makes everything move, let's say. So without batteries we cannot do anything, we can do very little. So this is a simple version of the battery. This battery is divided into two compartments. We have an electrolyte solution, we have a salt bridge, two different types of metals having different reduction potential. One is called the cathode, the other one is called the anode, and the difference of the potential of the two semi-reactions occurring in the two beakers is what we call the voltage of the battery. Measured in volts from Alessandro Volta, who invented the first type of battery. Inside the battery there is an electric field because there is a gradient of potential. This symbol nabla indicates the gradient, and in one dimension basically is the derivative of the function of which we are computing the gradient according to the distance, the coordinate of space. This thing would be useful later, just to remember that the gradient in one dimension is the first derivative in space. So, without going into the electrochemistry of the battery, we must say one very important thing. It's an approximation, but it's a good approximation. The battery for us, the ideal battery, is a source of constant voltage. Source of constant voltage. This is the battery. In other words, the job of the battery, the electrochemistry, all the reactions that are happening inside these two beakers do things in a way that no matters what you connect here. So here we close the circuit. The voltage between the anode and the cathode, VA, VB, so VA minus VB, this is delta V, remains constant. The battery do this. So it's not completely true, but let's say that an ideal battery will do this. Then we will see how we can model a real battery, so a battery that cannot do this. But for the moment, let's consider an ideal case. So what's between the two terminals of a battery? This thing we put here. We can put different things. Of course, if we put a piece of insulator, we know that no current can flow because it's very hard to accelerate electrons in an insulator. We need a lot of energy, but the energy was connected to the voltage, so we need a very big delta V, and it's difficult to produce it. Maybe it's not present in the battery. So nothing happens if we put an insulator. Let's try to put a piece of metal, then the current will flow. So we want to understand how it can flow. So we can do a very simple model, which is not quantum, so nothing to do with quantum mechanics. It's called the Drude and Lorentz pinball model. And it's very simple. So it considers atoms as nuclei. These are the nuclei of a metal. So in electronics, basically, when we speak about metals, we speak about copper. And the electrons are small balls like this in this model. They are accelerated by an electric field. So here and here, let's say we put a battery like this, sorry. This is the symbol of the battery. This thing, oops. This thing here, with the positive side and the negative side. So here electrons want to reach the other side because they feel an electric field that are pushing them moving, but when they do this, they hit against an ion, which is the nucleus of an atom without an electron. Then they hit another one, they maybe they even go back, but then they do like this, and so on. So this path that makes electron moving from one side to another one is difficult. It depends on how this kind of pinball bounces are happening. So the model can be expressed with some quantities like the mass of the electron, the charge of the electron, the density number of the electrons, how many electrons per volume there are, and one parameter which is called tau. It's a time. It's called the relaxation time. All those things together, multiplied by the electric field E, which is due to the battery, produce a current density, actually, J. So this thing Given that we choose the type of material, and this is reflected in a way that all those quantities here are defined, this thing is saying that the current density is proportional to the electric field, and this thing here is called G, conductivity. G is the conductivity. Okay. So basically what is written here is that J equals G E. The materials that can be described by this law are called ohmic conductors, and this is the, I put between parentheses, local Ohm's law. Okay. So this conductivity G can also be expressed as another quantity 1 over rho, where rho is called resistivity. Then in place of the electric field we can put the expression related to the gradient of the voltage, and so if E equals dV over dx, in a small piece of material having a certain resistivity rho, this thing is something like delta V over the length L. You have to imagine something like this, a small device having resistivity rho inside, so this is a resistor, and we are here. Then because this we said is the current density, which is the current per square meter, so imagine that this thing is a little cylinder like this one. Here we have some resistors. As you can see, they can be pretty small. Then imagine that there is something in these cylinders, so they are like this. So this cylinder has a cross section. The area of this cross section is S. All the charges are moving like this. And this is creating a current density. And if we integrate this current density across this section S, and by integration, if these vectors are perpendicular to this cross section, it means just a simple multiplication, then we get this. So this thing, by definition, we call current, measured in amperes. And if we just make some substitution, then we can realize that we can group things together, this thing, and we call this R, which is called resistance. So R is the resistance of this device that we call resistor. and it's a constant value. In commercial resistors, this value is written with a color bar code. We will mention about this color bar code. And basically here the physics stops for us. So we don't ask ourselves how a manufacturer can be able to manufacture this type of things. For us, this thing is a black box, and I introduce for the first time this terminology in this course. We will use this order also to see other type of black boxes. So for us, the resistor is something like this. We don't know what's inside, but the manufacturer give us a model and a value for this model. For us, this value is that if you apply a voltage V to this device, there will be a current I flowing in it according to this model. V equals R multiply I. And then you need to sculpt this law in your mind, because it's super important, very simple but very important. Just to remember it, I will write it here on my hand. So now it's impossible, it doesn't write. I write it like this. V equals Ri, because if you want to do electronics, you have to remember this forever. Okay, so that's it for today. We will continue next time.